This lecture. Today is from today a new timetable. We are having one afternoon class, especially on today, that is Thursday. So after lunch it will be difficult, but somehow we have to bear with it. So in the last class, we were discussing about the batch reactor. There are two types of batch reactor: constant volume and a constant pressure. So at constant volume, what will happen if you want to keep the volume as a constant? Then if the what do you call the products are increasing in volume, then the pressure will increase. That's what I mean to tell. So if you are maintaining at a constant volume, generally the pressure will change. And if you want to maintain at a constant pressure, then this to maintain the constant pressure, volume will increase. That is what here in this diagram it is being shown. Okay, we'll see more about this volume increase a bit later. Let us do some derivation based on the constant volume. If there is a constant volume, then there can be a change in the pressure, right? So what is a batch reactor first? Batch reactor is like this: a vessel in which a stirrer is there. This stirrer stirs the entire components or raw materials so that uniformity is achieved. There is an input, there is an output, and there will be a pressure indicator to show any changes in the pressure. So in batch reactor, generally liquid phase reactions, generally you use liquid phase reactions in the batch reactor. There will be no input, there will be no output. Generally, at time t is equal to 0, your raw materials, if A and B is giving you product, that both A and B will be put together inside, and then you start the stopwatch. That is, the reaction will start. So you will allow for some time for the reactants to react. After some time, maybe around 10 minutes or even 15 minutes or even 1 hour, after that particular time, you will remove these products and then do what do you call separation of unreacted materials, all that. So generally in a batch reactor, there will be no continuous input, there will be no continuous output. This is a simple batch reactor. Later we will see flow reactors where continuous input is there and continuous withdrawal of the products also will be there. But in a batch reactor, there is no continuous input and there is no continuous output. Whatever you are putting, you are making it to react for some particular time. After that time, you will remove the products or raw materials which is present in the reactor. So any reactor will have both advantages and disadvantages. So batch reactor is having a lot of advantages because it is simple in construction, not much of equipment details is required, simple to operate because there is no moving part, especially only this particular thing, that is stirrer. It has flexibility of operation. Cost is relatively low compared to that of flow reactors. Requires small instrumentation and less supporting equipment. One important thing is gives higher conversion for longer periods of time inside the reactor. It's a very important what do you call point, high conversion. You remember, as long as the raw materials or the more the time the raw material stays inside the reactor, then more will be the conversion. That is one thumb rule. So if you want more conversion, generally you have to make the raw materials to stay in the reactor a bit more time. So here in batch reactor, you are allowing that to happen because you are allowing some fixed amount of time for the raw materials to react. Therefore, the conversion in this reactor will be higher. Right? That is what I mean to tell this. Give a high conversion for a longer periods of time in the reactor. So when you do a problems with the flow reactor and even the batch reactor, that time we can understand for a fixed amount of time what reactor will give you more conversion. That we'll see when we do the problem. Right? Disadvantages, not only advantages, there will be a lot of disadvantages also. One is high labor cost per unit volume of the production. Because for every volume of the production, there will be what do you call a labor to what do you call feed the reactants inside the reactor, to leave or to separate this particular products from the labor is required to separate this products from the reactor. Again, you have to clean in between every batches. So lot of equipment personnel is required. That is why we call it as high labor cost. Whereas in continuous reactor, in between there is no batches there. So the process is continuous. So not much of personnel is required. So especially batch reactor, this is one biggest disadvantage is high labor cost. Requires considerable time to empty, clean out and refill. That's what I just told here. So each batch will have some time to empty the reactants or products, clean the reactor and again refill the raw materials. Whereas in continuous reactors, the process is continuous, so not much of time is required. Other important is quality control of the product is very poor because you are allowing the products to react for some amount of time. In between that particular time, you are not making any effort to see the quality of the product. So if you want a purity component, so this will never give you a purity component. Whereas continuous process, you continuously monitor the purity. Based on the purity, requirement of the purity, you change the operating conditions. But here you are not doing anything like that. The fourth one is large scale production is difficult because it's a batch process. So once the batch is over, then again another batch will be done. So if you want for a large scale production, you require continuous reactors. So this is some of the example, what do you call advantages and disadvantages of the batch reactor. That does not mean that batch reactor will never be used. Batch reactor is useful, especially for liquid phase reactions, and a lot of pharmaceutical companies they use batch reactor because every what do you call drug, whatever we are using, it will be prepared in a batch process, not as a continuous process. For that, you can see the tablet at the back. They'll give you a batch number, time of when it was done, all that. Not only that, even the food items, everything is a batch process, not a continuous process. The what do you call the filling, everything is continuous, but the equipment, the product which is coming out, they do as a batches. Understand? So that is what disadvantages and disadvantages. Now let us go and see how we can derive a performance equation for this. So if you want to design an ideal batch reactor, generally what do you mean by design? What I mean by design is nothing but how to find out the conversion after some particular time. Now you are allowing the raw materials to react inside the reactor for some amount of time. So now let it be 5 minutes you are keeping inside the reactor. Now, after 4 minutes, how much is the conversion? How do I know? That is what we will do by the design. That is otherwise called as performance expression. So if the batch reactor is ideal, so all reactors generally it is non-ideal. We use ideal conditions to compare our performance. Ideal reactors are generally all reactors are real reactor because there will be some non-idealities. Though in your calculation part, if you see that you get a conversion of around 90%, but in reality you may not get it. For a particular volume of a reactor, if you are expecting a conversion of around 90%, in reality that 90% is for that particular volume of a reactor, it may not come because non-idealities will be present. Just like non-ideal in the sense, human being, we are having two eyes, two legs, two hands, but some people may not have one hand, one leg. So you have to live with that non-ideality. So ideal batch reactor is not there. It's only just to compare only we'll use. So let us do the design for the first ideal reactor. Then we will see in the fifth unit how to deal with the non-idealities present in the reactor. So ideal reactor, if the conversion is 90%, but in actual case, it may be much lesser than that. How much it will be lesser, that we will see in the fifth unit. That is what I mean by non-ideal study. We'll see what are the non-idealities present inside the reactor and then see how we can find out the conversion from that non-ideal reactors. So if you want to have a design equation, we need to do a material balance around this. Again, material balance and energy balance already you might have studied. Here it will come because if you want to design a performance equation, a material balance is required. Since you are going for a constant temperature, no energy balance is required. But in fourth unit, especially if it is a non-isothermal case, especially batch reactor, you have to write energy balance also along with the material balance. So right now we'll use only the material balance. So material balance of A on a mole basis at any time t. A is a reactant. A is giving you some product. Let us assume that here there is a reaction which is A is giving you R. That is the product. Let this is some K, rate constant. So A is giving you R. So I'm writing the material balance based on the raw material A on a mole basis. So mole basis in the sense I'll get a unit as moles per time, right? Moles per time because any time I'm 1 second. Hello. Class. Sir, class ended. Sorry. So we write the material balance. Already you might have studied in what is this process calculations. Input should be equal to output plus disappearance plus accumulation. Disappearance will come because the reaction is happening. If there is no reaction, then input is equal to output plus accumulation. That is what the steady state material balance or unsteady state material balance, because accumulation is coming. You are writing a unsteady state material balance. So here in this batch reactor, input of A, output of A, again disappearance of A by chemical reaction plus accumulation of A within the reactor. Why you are writing like that? Can anyone tell? Is it material balance makes some sense here? This is the expression. It's a very important expression. Now, what does this make? How we have to write this? So I'll give you one example so that you will remember without any difficulties. Everyone is having a bank account, right? Everyone is having a bank account, right? So let us take bank account. So if you want to write the material balance for the bank account, material balance in the sense how the cash is flowing outside, input, how much you are putting or how much you are removing, whatever you want, is how much you are withdrawing. This is withdrawing. Disappearance comes because you are having some, what do you call, debit card charges, or some monthly, what do you call, things which the bank will take from you, right? Yearly or 6 months once. Then what is accumulation? Accumulation is nothing but at every 6 months or 1 year, bank will give you interest. INTRE, right? INTRE. Sorry. INTREST. So some amount your money will be earning. That is nothing but the accumulated. That is because of the interest. I'm just giving an example. Don't think that accumulation is always interest, right? Just to understand this, I'm giving this example to make you understand. Disappearance is here because of the reaction A is getting disappeared. That is nothing but your money is disappeared or withdrawal by the bank itself without your approval. Debit card charges, if you are having a debit card, they'll take debit card charges without your approval at all. Every 6 months, they'll take some 90 rupees or 100 rupees. Output, withdrawal, this you have to sign. Right? If you sign only, they will give you money. So this is how the material balance is. So accumulation is nothing but which is being what do you call, generated inside or whatever it is. If you are giving that example, right? So here in batch reactor, input is 0 because there is no continuous input. Only input you put, output you are taking out. But with the time, there is no input. With the time, there is no output, continuous. I mean continuous. So if you do that, this is 0. This is also 0. Input of A is 0. Output of A is 0. So you are left with the two terms, disappearance and accumulation. So if I do that, disappearance is nothing but minus accumulation because everything is 0 here because since this is 0. So disappearance is accumulation. Disappearance means disappearance of A. How the A is disappearing is nothing but A is giving R minus RA is nothing but minus 1 by V into dCA or dNA by dt. Correct. This is the rate expression. Now minus RA is nothing but disappearance of A is 1 by V because here I am writing for a constant volume and constant temperature. So DNA is nothing but number of moles changing with respect to the time. That is what we want. Disappearance. How much is the disappearance? Is nothing but moles per time. So DNA by dt is nothing but RA into V. That is what I am writing here. Minus RA into V. This minus is this because disappearance. Right? We are writing for the disappearance. So minus RA into V. Because we want only this minus RA into V. You multiply here. Any doubt here? Disappearance, how you are getting the term? Then the accumulation. Accumulation is nothing but how much is changing. Number of moles, how much it is changing. DNA by dt. DNA by dt. So if you are writing a material balance, each and every term should have the same unit. That is how we have to write the material balance or even the energy balance. So energy balance, joules per second should be the unit, joule per second. Because rate of energy input, rate of energy output. Here, mass, how much is the mass input per unit time? So here you are writing in terms of a mole basis, or you can write in terms of a mass basis also. Mass means kg per second you get. Mole means mole per second you get. Mole per second or per minute or per hour, whatever it is. Moles per time. That is why we call it as a rate. Right? Any doubt in this two expressions how you are getting? Yeah. Some of you can give feedback. No? Don't want
So
to
can
give?
you repeat the disappearance by chemical reaction one again?
Yeah. Mm, shall we use this? Yeah, I'll use this. Now you see this is the reaction. I'm just writing here. A is giving you some R product, right? Hmm. So I'm writing rate minus RA is equal to K times some CA, right? Sorry. This I'll write a bit later. Let us not write here. Minus RA is equal to minus 1 by V into DNA by dt. Correct. That is equal to K into Ca. That's okay. If you want, you can write here. Now, this we know already we studied based on the volume of the fluid inside the reactor we are writing. We are assuming it is constant volume minus DNA by dt is nothing but number of moles disappeared, minus is nothing but disappeared, divided by time. So minus RA into, if I cross multiply this into V is nothing but minus DNA by dt. What is minus DNA by dt is nothing but minus is disappearing. So number of moles or moles disappearing, moles disappearing per time. So moles disappearing per time is nothing but minus RA into V. That is what I just put here. That is what here. Minus RA into V is nothing but moles disappear. This is what, right? End it out. Accumulation is nothing but positive DNA by dt. Minus DNA by dt is disappearance. Plus DNA by dt is nothing but accumulated. That means how much is increased. Correct? Or formed. Accumulated is nothing but formed. Whatever way you want, you can give. Any doubt? Shall I go for the next one? Now we have to equate these two. We have to equate these two, right? Now still let us go to this. Now if you equate disappearance is equal to negative of what is that other one? Accumulation. What is disappearance? Minus RA into V is equal to accumulation is nothing but minus is there DNA by dt. Correct? DNA by dt. So now you see here. Okay. So here one important thing is what is Na? Na is the number of moles of A. Na is number of moles of A. Na is Na naught into 1 minus Xa. This is an important expression. What is this expression? Na naught is the initial number of moles. Initial number of moles. Na is the final number of moles. Xa is the conversion. Conversion of A. I'm writing only for A because my reaction is A is giving you R. So I'm writing based on A. So Na is the number of moles of A at final after temperature T or time T is initial number of moles into 1 minus Xa. Xa is the conversion. So initial number of moles is constant. Na will change with respect to the time because if you react more amount of time, then with the time the conversion changes. Therefore, Na will change. So this is derivative d by dt of Na. If you substitute this here, then what will happen? Sorry. So if I substitute, let me write minus Ra into V is equal to minus d by dt of Na, right? Na is nothing but Na naught into 1 minus Xa. Okay. What is Na naught? Na naught is the initial number of moles, which is a constant. It is not changing with respect to the time. At time t is equal to 0, that is the constant, right? So let you take this outside the integral. You can take outside the integral. Am I right? We can take outside the integral. Therefore, minus Ra into V is equal to minus Na naught, right, into d by dt of 1 minus Xa. 1 minus Xa. Again, let you again. Then minus Ra. So minus Ra into V is equal to minus Na naught into d by dt of 1 minus Xa. So it is nothing but d by dt of A minus B. We can write as differential of A minus differential of B. Correct. So differential of 1 is 0. Minus Xa is minus dxa divided by dt. Any doubt here? 1 minus Xa, because t you are differentiating with a t. Therefore, this is a constant. Constant will have 0. Minus Xa, differential is dxa by dt. Correct. Minus will be there. Minus into minus becomes positive. Therefore, Ra into V is equal to Na naught into dxa by dt. Na naught into dxa by dt. Correct. Any doubt here? Any doubt? So,
No,
Na naught is constant. So we write as V by Na naught is equal to V by Na naught is equal to 1 by minus Ra into dxa by dt. Can we write like this? I'm just shifting this here, shifting this here. Correct. So you can keep like this, or if you want to still do, you can do. That is what I'm just show you now. Now you see here, Na, because Na is Na naught into 1 minus Xa by dt. So if you differentiate this, we get minus Na naught dxa by dt. Correct? Because here minus is there. That is what I just put here. Minus, right? So we are doing only this. This will have Na naught minus dxa. Minus I put here. That is why this minus is coming. Yeah. So if I substitute in the terms, minus Ra into V is minus of minus. This minus into minus becomes positive. If you rearrange, we can write dt. That's what just I wrote here. We can put dt also. Dt is equal to, that is the time for the reaction. We can take it ulta here and then write as like this. Na naught into dxa by minus Ra into V. Can we do that? Can we do that? That is what just here. Again put here. So from this, if you want to write dt, dt is equal to this. You are taking this side. Rest of the thing you bring this side. Therefore, dt is equal to Na naught, because this will go up, Na naught by V into minus Ra into dxa. Correct? Correct? Because this we are bringing down, this we are taking up, this is keeping like that, dt you are taking this this side, correct? That is what I just wrote here. That is what I just wrote here. Na naught, that is what Na naught dxa by minus Ra into V. Dxa by minus Ra into V. Okay. If you want to write in that the same terms, then you put dt is equal to Na naught into dxa by minus Ra into V. Minus Ra is the rate of the disappearance. V is the volume of the reactant or volume of the fluid. Xa is the conversion. Na is the initial number of moles. Now, in batch reactor, we should know what is the conversion after some particular time, right? So, for that, what you have to do? This is dt. So, you have to integrate this. So, integrate this equation. If you integrate the equation, integrate between the limits of t is equal to 0, t is equal to t. So, at t is equal to 0, what will happen? This xa, you are differentiating with respect to or integrating with respect to xa. Xa will be 0 because at time t is equal to 0, there is no reaction. Xa also will be 0. At time t is equal to t, your xa becomes xa, right? That is the limits. Now, if you differentiate, integral of dt is t. So, the upper limit is 0, sorry, lower limit is 0, upper limit is t, is equal to Na naught is constant. You can take outside the integral, Na naught, right? So, V is also constant because we are using constant volume. Therefore, I can take V also outside. Integral 0 to xa dxa by minus Ra. We don't know what is this minus Ra because minus Ra will change with the k into Ca. Square can be coming, 1.5 can come, or k itself will change. We don't know. So we cannot take outside the integral. So keep it inside the integral. Now what is Na naught by V? V or V naught, initial number of or initial volume or final volume, whatever. Na naught by V is nothing but C, Ca naught. Therefore, if you substitute the limits, T is equal to Ca naught into dxa by minus Ra integral 0 to xa. This is the final form of the equation. Using this equation, if you know the rate, we can find out what is the conversion at any particular time. After 15 minutes, what will be the conversion? After 30 minutes, what will be the conversion? Knowing your initial concentration. Knowing your initial concentration. Either you can keep in terms of this or Na naught. If he gives you in terms of moles, then also you can use this equation. Yeah, this is the derivation. Any doubt in derivation? Yesterday you are talking about you want to write it all that. You know, this derivation takes lot of time to write. It's not that because we have to complete the syllabus. Very vast syllabus is there. What till now I taught is the tip of an iceberg. These derivations are all very simple, only just differentiation and integration. You are going to get still much difficult derivations, right? So in that process, I just skipped that. But you want me to write, I will write. I don't mind. But again, if I'm not going to complete the syllabus, then you have to read difficult parts. Since it is a simple part, I skipped. But you want me to do it, I will do it. I don't mind. But at a cost again, because we have to see the time. First unit itself, in the first class itself, I told I require more than 20 to 25 periods. Because based on this Ra, for a first order, you will get different expression. For a second order, you get different expression. If the equation is reversible, again, you get different equation for this, right? Okay. Okay, anyhow, thanks for pointing out that, but I'll try to write on the board as at least one thing I'll try to do. I know it is difficult to follow for you in the online. But that's why I just uploaded the notes and everything. But you want me to write, I'll write. Okay. So thanks for pointing out that. So I'll hope we'll write for some time, right? Yeah. Now this see here, xa is 0, at time is 0, xa is xa, at time t is equal to t. So integral 0 to t, na naught, integral 0 to xa, dxa by minus Ra into v. Since v is constant, I am taking outside the integral. That is what? T is equal to na naught this. So if you want to keep in the number of moles, this is the expression. Ca naught, T is equal to Ca naught, integral 0 to xa, dxa by minus Ra into v. Either you can keep here or Na naught by V, you can write as Ca naught also. That's up to you. This is the general design expression for the batch reactor. Right? That is what here I am writing. For a constant volume batch reactor, V is V naught, that is the initial number of moles is equal to the final volume. Na naught by V naught or V is equal to Ca naught. Ca naught dxa by minus Ra. Either you can keep in terms of XAs or you can keep in terms of CS also. How we are going to get this expression, I'll show you here. I'll write here itself with your permission. Now, either you can stop using like this equation or you can use interest of conversion. You can put instead of concentrations itself. How we do is, here one more important thing is, since we wrote Na is Na naught into 1 minus Xa. This is final number of moles is initial moles into 1 minus Xa. Xa is the conversion. So like that, if you want to write by volume, final volume or initial volume, which is going to be constant, then we can write Ca as Ca naught into 1 minus Xa. Ca is Ca naught into 1 minus Xa, correct? Right? Like the same thing. Final concentration is initial concentration to 1 minus Xa. Now we want Xa here, right? We want Xa. So we can write Xa, Ca by Ca naught is equal to 1 minus Xa. That is equal to, if you write Xa as 1 minus Ca by Ca naught. Can we write like this from this equation? From this equation. Now Xa is 1 minus Ca by Ca naught. We can differentiate that dxa by dt or dxa. You differentiate this, then what will happen? If you are differentiating with respect to both sides, then this is a minus b. Differential of a, this is constant, therefore 0 minus Ca naught is constant. So I'll take outside that Ca naught. Integral differential of Ca is dCa. Correct? Can we write like that? So dxa by dt is nothing but minus dCa by Ca naught, or dCa is minus of Ca naught into dxa, right? We can write like this. If you want to put dt, you put dt. The same way, if you substitute here, instead of Xa, you substitute this 1 minus Ca by Ca naught and then do integral. Since you're changing this Xa to Ca, your limits also should be changed. Xa is 0. When Xa is 0, what will happen to? When Xa is 0, what will happen to your Ca? Ca is nothing but Ca naught. That is, at initial no conversion, your Ca, that is conversion of A, is nothing but initial conversion. When Xa is Xa, after some time, then your Ca becomes Ca or CAF. That is the final. Or Xa becomes XAF. Let it be final. So that is what you are substituting. When your lower limit 0, you are putting Ca naught. Ca naught is the initial concentration. Ca, Xa or XAF is CAF or Ca, whatever it is. That is equal to, this minus will come because there is one minus here. Yeah, if you substitute. that minus will come. Integral 0 Ca naught to Ca dCA by minus RA. This expression is the design expression for the batch reactor, especially for a constant volume in terms of conversion. This is in terms of conversion, and this is in terms of what is that? Sorry. This is in terms of This is in terms of concentration, and this is in terms of conversion. So you can write the design expression either in terms of conversion or concentration. Any doubt? Based on this, we have to do some problems. Any doubt in this derivation? Yeah, some feedback, please.
No doubts.
Can I go for next one?
Yes, sir.
If there is a volume change, this V you cannot take outside the integral. So we have to put like this. V naught into 1 minus exponential 1 plus sigma A XA. That is the how much it is being expanding. We'll see how much it will be expand all that. So if there is a volume change, we cannot take V as V naught. If there is a volume change, V is equal to V naught into 1 plus sigma A XA. This sigma A XA is called as the expansion factor. Generally, for a constant volume, this will be 0. Therefore, V becomes V naught because this is 0. This is 0. V naught into 1 is V naught. But if expansion factor is not 0, especially for volume change, then V and V naught will change. This you have to put here. Then this extra term will come in the inside the integral. There will be two terms in the integral. Earlier we are having only one term. Your life becomes simple because minus RA itself you have to write as K into CA. So if the integral, if you write here K into CA, 1, 2, 3 terms, integral of 3 terms, 1 by. You have to do integration by parts. Am I right? So 2 itself is difficult. UV, U into differential of, you know that the integral of UV, right? 1 by UV and all. Right? Integration by parts. You don't ask me all this integration by parts and all. I'm not a mathematics teacher to teach all this now. Right? You have to know that. So the moment more terms are increasing, then the integration becomes very troublesome. You have to do by what do you call partial fractions. That we'll see, right? So as long as possible, we try to reduce the number of terms. That is why we make it as V is constant. If you are not making V as constant, this extra term will come inside this, and the integral for this becomes very difficult. So this kind of equation is called as the variable volume design expression, right? This expression can be used both for isothermal and non-isothermal cases. Now, since we have this equation, this is the performance equation. We didn't substitute still what is minus RA. This minus RA will change as per the order of a reaction. If you substitute the order, first order, you get one expression. If you substitute the second order, you get one more expression. If you substitute the zeroth order, you get one more expression. If you are substituting a reversible equation, like A is giving you R and R is giving you A, then your minus RA again, it will be changing. That we will see now, right? So here one important thing is this particular thing. What is the expression we are getting? T is equal to Na naught by V into integral 0 to xa dxa by minus Ra. This is the expression which we got, right? This is the design expression for the constant volume batch reactor. Either you can write like that, or T is equal to Ca naught, because Na naught by V or V naught is Ca naught, integral 0 to xa, integral 0 to xa, yeah, dca, sorry, dxa divided by dt. Either you can write like this, or you want to change these limits. Instead of xa, if you want to convert to ca, then also we can write as c is equal to t is equal to, that is what in the previous one we got. This is the expression. T is equal to minus ca naught to ca dca by minus ra. That is what I'll write. T is equal to minus integral ca naught to ca dca by minus ra. Right? So how to write this in terms of what do you call graph? Because this integral finding is not that easy. This integral finding is not that easy. What we have to do is, now you see, I'm drawing a graph between y-axis is minus Ra into V, and x-axis is xa. X-axis is xa. So y-axis is this, x-axis is this. Then what will happen? The area under the curve. Now this is C. If you want to do this, again I'll write here. T by Na naught, T by Na naught is equal to, I'm just rewriting this equation. T by Na naught, let it be like this. What you do is integral 0 to xa dxa by minus Ra into V is equal to T by one second. You have to write like y is equal to mx. So y is this minus Ra by 1 minus Ra by V, because this is an integral. Integral you can find out simply as area under the curve. Area under the curve. Correct. So if you draw a y-axis minus 1 by Ra by V into xa, because with xa, so area under the curve will come like this. Area under the curve will give you this integral. You know that, right? Integral is nothing but area under the curve, whereas differential is nothing but the tangent to the curve, right? So area under the curve, this entire area will give you T by Na naught. Since Na naught you know, we can calculate T, time for the conversion, final conversion. You want 90% conversion. So this is the 90% conversion line. You draw here and find out what is your thing, and then find out for this particular thing, you draw, find the area under the curve. You can find out how much is the time required for that particular conversion. You can do one more way, minus 1 by Ra on the y-axis and xa on the x-axis. Again, area under the curve will give you T by Ca naught, because Na naught by V is nothing but Ca naught. Either way you can find out time for a particular conversion, whatever conversion you want. If you are having concentrations, then again, you can draw Ca on the x-axis, minus 1 by Ra on the y-axis. Then what will happen? This is 1 by minus, this is on the y-axis. This is on the x-axis CA. So CA naught is having more concentration. CA is having less concentration. This is minus 1 by RA. Your curve will come like this. Going from CA naught, whatever CA is final, you can put a line and then find out the area under the curve. This will give you the time for that particular concentration, whatever concentration you want. So CRE problems you have to do with a lot with the graph. So next classes, when you are doing a problem, keep the graph sheets handy. Keep the graph sheets with you. Without graph sheet, you cannot find out anything in CRE, because the wall area under the curve you have to find out. You have to draw the curve and then you have to find out the area under the curve. Again, finding the area under the curve, again, you have to see how many squares are there, and then you have to do some averaging and then find out the area under the curve. Area under the curve will give you the time or the volume of the reactor. If you see the flow reactors, will get the volume of the reactors. So please keep what is this graph sheets, especially 1/4 graph sheet. You keep one graph sheet, you make as 4 parts, and then you can do that what do you call graph, and then paste in your notebook itself. Okay. Yeah, any doubt now? Yeah, this you will understand when you do problems. We'll do problems, that time you will understand. So because this integral calculation is not that easy, because this minus RA becomes very tricky. If there is a squared term, if there is a cube term, it's not that easy to calculate this integral. I will show you how difficult it will be. If you are not using this graph sheets, how difficult it will be, I'll show you in the derivations. Shall I go for the next one, ma? Shall I go for the next one?
Yes, sir.
Now let us use. Now let us take this minus RA. Let us use this minus RA. Let us take one. We have to write minus RA, right? This is the expression. T is equal to Na naught by V into integral 0 to XA dXA by minus RA. This is the batch reactor expression, right? We don't know what is this minus RA. Then only we have to substitute here. For every reaction, there will be a different rate. So let us use a irreversible unimolecular type first order reaction. A is giving you product. A is giving you product. Let this is some constant K, that is rate. So if I write this, minus RA is minus dCA by dt is nothing but K into CA. Correct? How you am writing minus dCA by dt is nothing but minus RA is minus 1 by V into dNA by dt, that is equal to K into CA. This is what we wrote. This is the first order. Therefore, you are writing 1. Now, since it is constant volume, we are writing Na by V as Ca. Therefore, minus Ra is minus dCA by dt is equal to K into Ca. Correct? Ca is the first order. Now, we write these two equations because minus dCA by dt is K into Ca. You take all the Ca terms to one side, other terms to another side, then what will happen? Minus dCA by dt is K into dt. Correct? Now you have to integrate this again. Integrate this equation because derivative, because concentration is changing. Again, the change of that concentration divided by that concentration. So how you will put? You are changing with respect to the dt. Therefore, time t is equal to 0. Time t is equal to t. At time t is equal to 0, what will happen to your Ca? Because Ca is Ca naught. At time t is equal to t, Ca becomes Ca. So that is what I am putting. The limits. CA is CA naught at time t is equal to 0. CA is CA at time t is equal to t. So if you substitute the limits, then what will happen? Minus dCA by dt, CA naught to CA. There is a minus. So you can change this lower limit and upper limit. Therefore, CA naught to CA, dCA by dt is K times, K is constant because you are using it is isothermal. Isothermal. If it is isothermal, you can take K as constant. Otherwise, you have to integrate again the K. This is what we will do in fourth unit. Now let us, for a isothermal case, this is constant. So we are taking outside the integral, integral 0 to t dt. Now what is this? dCA by dt integral is nothing but ln. So minus ln, here one negative is there, sorry, because this negative is carries here. Minus ln. Now a ln CA, if you substitute the limits, CA by CA naught is K into T. So you want to calculate K. K is the rate constant. 1 by T into ln CA naught by CA. Because minus is there, you put CA naught by CA. Correct? So this is the expression, or if you want to calculate T, you can do T is equal to, that is time, is equal to 1 by K ln CA naught by CA. This is also an expression. Either you can keep in terms of the conversion concentrations, or you can keep in terms of conversions also, because we know already that CA, in terms of conversions, we know already CA is equal to CA naught into 1 minus XA. From that, instead of CA, we can put in terms of conversions also. That is what we'll do. Minus dCA by dt is K into CA. But CA, if you write in terms of this, then differential of CA is nothing but CA naught into 1 minus XA by CA again is CA naught into 1 minus XA is K into dt. You are taking CA to one side, dt to another side. So dCA by dt I wrote. So if you differentiate this, CA naught is constant. So you can take outside the integral. That CA naught and this CA naught gets cancelled out. Minus differential of 1 minus XA is dXA. There is a minus here, there is a minus here, dXA. 1 minus XA. This because there is no differential here. Is equal to K into dt. Again, if you substitute the limits, XA is 0 when t is 0. XA is XA when t is t. Then if you substitute, you get this final form of the equation. Here again, t is equal to 1 by K minus ln 1 minus XA. This is the final form of the equation for a first order equation. 1 by K minus ln 1 minus XA. This is in terms of the conversion, or you can put in terms of the concentration also. You can put in terms of concentrations also, that is right. That's up to you how you want to put it. So you can put in terms of conversions, concentrations and conversions. This is for the first order reaction. If there is a second order reaction, we get square here, correct? Now minus dCA by dt is K times CA square. Right. Now minus dCA by dt, CA square is K into dt. Now if you differentiate this, then differential of 1 by x square is nothing but minus 1 by x. Understand? So this is where it will change. Now that is what I'll show you in the next class when you are having square. So minus dCA by CA square is K into dt. If you substitute the limit, this is nothing but integral of 1 by XA by dXA, or dx by x square is minus 1 by x. So if you substitute the limits, you get 1 by CA minus 1 by CA naught. Whereas earlier you are getting differently. So with the order, you get different expressions. You see here, for a second order process, you are getting K is 1 by T into 1 by Ca minus 1 by Ca naught. Whereas for the first order, you are getting T is 1 by K into ln Ca naught by Ca. If there is a third order, you get still one more equation. That is why I'm just putting minus RA. So minus RA itself is very difficult to find out because it's a rate. That is why integral of minus RA generally will go as this graph. That is why graphs are very useful in not only here, even in process calculation, you use a lot of graphs. So in CRE, we'll do the problems, especially this RA calculations. We cannot find out. That is why we draw a graph. Area under the curve will give you that integral, right? That it will be much easier. Yeah, I think I'll stop. It is already 2 o'clock. I'll stop. Any doubt, ma, today? Is it okay? You want like this writing? But you see one small derivation, I took 1 hour. It's a very small derivation. It just A is giving R. If there are two reactants, A plus B gives R, then the entire goes for a toss. Because you won't get that simply. That integral, you have to do integration by parts. Okay. Yeah, we'll see that in the next class. Any doubt here? Yeah. Any doubt? Shall I stop the recording?